Okay, so we're looking at free fall. We're looking at specific instances where objects are thrown up, kicked, hit, shot up into the air. With this, the initial vertical velocity is some positive number. Okay, we're getting away from these dropped examples where the initial velocity or initial vertical velocity is 0. With free fall, a couple things. Remember that the only force acting on an object that's freely falling is gravity. Okay, that's the only force. So we're assuming little to no air resistance, which we call negligible air resistance. And so if the only force acting on the object is gravity, and that's a constant force, then we're going to have a uniform acceleration. And we know that that uniform acceleration near the surface of the Earth, we call that g, that's negative 9.8 meters per second squared. Okay. Now our big question in the lab that you just did with the ball that you threw up into the air is the ball freely falling on the way up and on the way down? Okay. So let's look at that. So if we take a ball, so here's my ball, we're going to throw it up into the air with some initial vertical velocity. It's going to hit the peak, so here's the peak of its trajectory, and then the ball is going to come back down, let's say, to that same initial vertical position. I want to look at the SPARKview data to kind of give you some more information here. So this is the position, vertical position versus time graph for the ball that's thrown up into the air. If we look at the instantaneous slope, that would be the instantaneous velocity. So here you can see the instantaneous initial velocity is 2.76 meters per second. As the ball travels up into the air, you can see that that velocity is decreasing, which makes sense because the ball is slowing down. At the peak of its trajectory, you can see that the instantaneous velocity is very near 0. It's going to stop for an instant. And then on the way back down, the velocity is negative because the ball is moving in the downward direction, but the magnitude of the velocity is increasing till we get right there. Okay, so there we have the final vertical velocity right before it comes back to that same vertical height or position, and notice it is the same in magnitude as our initial vertical velocity. So what we can say here is we can say that our initial vertical velocity, we're just going to say 2.7, is positive meters per second. The velocity at the peak up here was 0 for an instant, and then our final vertical velocity here is negative 2.7 meters per second. And of course, the ball is slowing down on the way up and then speeding up on the way back down. Okay. I also want to look at the time because we didn't do this with the lab. So I'm going to use this cool little button here, and I'm going to measure the time to the peak. So notice the time to the peak is 0.300 seconds. And then we can find the time from the peak back to that original height, and that's 0.300 seconds. So the time from here to here is 0.300 seconds, and the time from the peak back to that original position is 0.300 seconds. So very much symmetrical, okay? Let's see. So based on what we know so far, do you think the ball is freely falling on the way up and on the way down? Well, let's look at some more stuff with our graphs. So now I am going to look at the velocity versus time graph, and I need to highlight the graph that I want to focus on. Okay, that looks pretty good. So you can see here that my SparkView just crashed on me. So we're going to try to open this again. Let's make that a little bit, okay. Okay, so you can see here the velocity. All right, some positive velocity, and then the velocity slows down, decreases until we hit 0 velocity at the peak, and then the velocity is negative on the way back down, and the magnitude is increasing, okay? But I want to show you, if we were to calculate the slope, which should represent the acceleration of the ball, the slope here is negative 9.72 meters per second squared, which hopefully you realize is very close to negative 9.8 meters per second squared. There is air in the classroom, so there's a little bit of air resistance. But I also want to point out that the acceleration is constant. So notice there, the instantaneous slope or acceleration is negative 9. There it's negative 9 meters per second squared. There it's negative 10. Okay, really close. Again, this is not perfect data. Negative 9 meters per second squared. Even at the peak of its trajectory, the acceleration is negative 9 meters per second squared. On the way back down, negative 9 meters per second squared. So that acceleration on the way up and on the way down and at the peak is negative 9 meters per second squared. So is the ball freely falling on the way up and on the way down? Well, let's look at our definition. On the way up, after the ball leaves our hand, is the only force gravity. Yep. Does the ball have a uniform acceleration? Yep. So remember, the acceleration here was around negative 9 meters per second squared. The acceleration at the top was around negative 9 meters per second squared. And the acceleration on the way back down was around negative 9 meters per second squared. So that uniform acceleration on the way up and on the way down and at the peak. Okay. The last thing I want to look at is the acceleration versus time graph. We're going to zoom in. And you can see here that and we're looking at this portion right here, that highlighted portion. You can see that the acceleration is around negative 9 meters per second squared, and it is constant and uniform. Okay.